Hello and welcome back to Calculus 3, section 11.6, Calculus of Vector Valued Functions. We know that calculus consists, and yes, I did spell it with K's because I can. So calculus consists of three concepts. We have the limits, we have derivatives, and we have integrals. Now, we define the vector valued function in terms of parameter t as a vector of functions. F of t, g of t, if we are in 3D, h of t, and then we can add more if we need more dimensions. It is not limited on how many dimensions we have to use. We can use any amount that is necessary for whatever application we are considering. Please remember that a dimension is simply an extra variable, right? That's all it is. So certain multivariable functions will have a lot of variables and more than 3 variables. Trying to think of some of the functions, but apart from stuff that we are going to do actually here, like distribution of density inside a 3D object, you have the 3 variables that describe the object, and then you will have the density, which is the 4th variable. Or you can think of the distribution of the temperature inside an object. So that would be, again, the 4th dimension, because you have x, y, z to describe the 3D object. But then I'm trying to actually, stay away from physics and engineering and maybe find something that it's. There was that one formula. It's related to fitness. That has your age and height and weight and calculate BMI. Okay, good. That's a 4D. Right? Because each one of the variables, height is a variable. Everyone has different height, right? And then we have the weight, and then we have the age, and we have the BMI at the end. So that's 4 variables, right? I mean, BMI is the variable that it's a dependent variable on the 3 input variables, height, weight, and age. So that's a 4D function. So it doesn't have to be something that we do in physics or engineering. Anything that has multiple variables where the variable represents a dimension. So now, how we're going to do calculus here? Well, it's going to be done term-wise. You are going to perform limit on each one of these functions separately, or the derivative, or the integral. So, do calc term-wise. I mean, yeah, or component-wise. And the lecture is over. I know, right? But then let's see if we can do an example that would make sense. And we haven't talked about position and velocity and acceleration yet, and it's calculus class, so you can't really escape that. So let's do say path for the particle is going to be given by the following formula. It's going to be 3 cosine t, 2t, and 3 sine t. So that's the path. What is this path? It's a helix. Very good. How would you draw this helix? I'm sorry? Very good. this helix will be wrapping around the y-axis. Yeah, very nice, very nice. So if we are to draw this, we can say this is x, this is y, this is z. The helix will, so cosine at 3, so it will be something like this. It will be wrapping around, it will start at 3 on x-axis, right? Because for t equal to 0, cosine is 1, 3 times 1 is 3, z would be 0, so it starts here. And it's going to wrap around y-axis. So technically, whatever this, right, is, it's wrapping around that axis. Good. Very good. Now, we know to find acceleration, to find the velocity, what do? We take the derivative, so that would be r prime of t. We take the derivative, and the way we take the derivative is term-wise. So what is the derivative of cosine t? Very good. What is the derivative of 2t? Nice. And what is the derivative of 3 sine t? Very good. Nice. What is speed? Absolute value of. Very good. Now, in terms of what we have over here, what do I have to do? Yes. We just figure out the magnitude. Speed is the magnitude of velocity. Now, guys, when you're on 78 or any other road, right, they say speed limit. They don't say velocity limit. Because, you know, everyone who's any amount normal would be driving with the flow, right? Remember, velocity is the magnitude, which is the speed, and the direction. Well, you should be going in the direction of the traffic, right? So, yes. So, that's why it's a speed limit, not a velocity limit. Because if it's the velocity limit, well, then you pick your direction too. It will be chaos, right? So now we have the square root of 9 sine squared t plus 4 plus 9 cosine squared t. When we put these guys together, factor out 9, it's going to be square root of 13. There we go. There.
What?
Sine squared plus cosine squared is 1. So you factor out 9. 9 times 1 is 9 plus 4 is 13, square root of 13. Good. Acceleration is the derivative of velocity. So acceleration, which is the r double prime of t, again, these are all vectors. We are going to have the vector of -3 cosine t 0 and -3 sine t. And that ends the problem. Ta-da! Bueno?
Sí.
Now, if I want to know exact position of the particle at time t equals to 5, I will plug in 5 in the path equation. If I want to know the velocity vector, I will plug in at 5 seconds, I will plug in 5 in the velocity vector. The speed is square root of 13, right? So the time will only adjust the time will only adjust the position, I mean the direction of the vector, but it will not adjust the speed, because as you can see, speed is always square root of 13, no matter what you plug in. Now, can I come up with a function when it would depend? Sure, right? The reason why speed is constant is because it's helix. And sine squared t, cosine squared t combined together to give you 1, so t's are gone. However, if I use instead of 2t over here, if I put 2t squared, right, then this would be 4t squared under the radical, and then obviously your speed would also depend on the time. So it depends what kind of function you have. And then acceleration is what it is. If you need to integrate vector-valued function, you will do the same thing. Now, for integration, please remember that when you do improper integral, you have indefinite integral, you have plus c at the end. Since your input is 3 different functions, you will have a vector c to add as a constant, which has c1, c2, c3 constants inside. So if we have initial point, we are able to compute the value for that. So let's see what I can have here. Say integral of 3t square root of t and 1 over t dt, and maybe we can set up that r at 0 is 1, 6 and negative 5, whatever. No, negative 5. 1, 6 and 10. No coffee. So now we integrate term-wise. The integral of 3t is 3t squared over 2. The integral of square root of t is going to be 2 root. No. T to, yes, that's what I said. Please pay attention. 3 halves divided by 3 halves. And then the integral of 1 over t is
0 to 1.
ln of t. Plus vector c, which is our constant. Now I can use the initial value to calculate all of this. So what do I have? I have 3 halves t squared plus 2/3 t to the 3 halves, no plus, comma, and then ln of absolute value of t plus c1, c2, c3 to equal to 1, 6, 10. And this is where I figure out, oh, all the t's need to be zeros. Oh, I can't do ln of 0. So this has to be 1. There we go. So now I can't do ln of 0. ln of 0 is negative infinity. So I changed initial condition over here from r of 0 to r of 1. So I can plug it in. So now I plug in 1 for every t, and I get 3 halves plus c1, actually equations. So 3 halves plus c1 is equal to 1, from where c1 is equal to negative 1/2. Great. Next one, when I plug in t equals to 1, that goes away, I get 2/3 plus c2 is equal to 6. So from here we can calculate 6 minus 2/3 is 5, and 1/3, that's 16 over 3. What happened?
How'd you do that again? Oh,
When you plug in?
This, and this is one equation. That's the first equation. And then this, and this is the second equation.
Okay. Have you the C1 and C2 value?
I'm sorry?
Solve the equation?
Yeah, you solve the equation, you
Oh,
get
okay.
each one.
Well,
Yep, yep.
They're plugging in for one.
One is for, you plug in 1 for t. And now the last one, when you plug in 1 for t, ln of 1 is? Very good, so C3 is just 10. So what is the answer? So answer is the vector 3/2 t squared minus 1/2, comma 2/3 t 3/2 plus C2. No, plus C2, that's 16/3. And comma ln of absolute t plus 10. So that will be the answer for this question. All right? So integration happened term by term. Each individual component of the vector is its own separate function, and I integrated each one separately without regarding any others. One side now, each one of these could be trig substitution, partial fraction decomposition, U substitution, by parts, right? You have all of the techniques from Calc 1 and Calc 2. Well, obviously put the basic integrals there, plus the C, vector C, because vector C needs to have the constant for the first component and the second and the third. So that's vector C1, C2, C3. And then you just equal that. Equal all of this, and you are done.
Why are you even talking about it?
Yeah, that's
like, why are you talking about it?
Why are you coming in my company?
Ooh! Because that guy caused me a lot of stress, and it just
I'd like to help.
the names.
Well, no, I'm
What's happening? What did he say?
They're talking about me.
Oh, he says he calls me.
I know, very exactly. That's why I brought my attention.
Oh, there is a formal.
He's a very interesting man.
So let's write the formal definition for the integration.
Guys, he's a pedophile. But no one knows. What? He's very.
Now
Yeah.
we have integral of r of t dt is the r of t is the antiderivative, the vector r, plus the vector c. Now if you want to write it in exploded form, you will write it as the integral of f of t, g of t, and h of t dt is giving us f of t, g of t, h of t, plus c1, c2, c3.
So the capital F just means integrated?
Capital, yes, capital letters are for antiderivatives, so following the same notation like in Calculus 1. Lowercase letters are functions, and the capital letters are antiderivatives, which means what you get once you perform integration.
What if you double integrate? Is it double capital?
Maybe capital and then next to it you brought up there.
And you calculate this term-wise, and that's that. Let's see.
Capital F. Don't laugh at my banana.
Who doesn't love a good banana?
So, tangent vectors. we know that we get the tangent line in calculus 1 when we find the derivative, plug in the point, right? So we compute everything at the point, and we are able to obtain the tangent line. Now we're going to have a tangent vector. The tangent vector is going to be, again, obtained through the derivative, and it's going to be obtained at the point, so we can find the tangent vector using the same procedure, or analogous procedure, from calculus 1. So let's take a look at the tangent vector problem. Say 16 from the book. We have the path function, which is the parametrization for the path, vector valued function r, given as e to the t, e to the 3t, e to the 5t. And we want to find the tangent line at time t equals 0. The way we would do this is, first off, I want to know the r of 0, right? Because we are computing at that point when time is equal to 0. So r is equal to 0 is going to give me 1, 1, 1. Vector 1, 1, 1, because e to the 0, e to the 3 times 0 is still e to the 0, and e to the 5 times 0 is still e to the 0. So they're all e to the 0, and they're all 1s. Then I need to find the derivative of r, because we want the vector, and so the tangent vector. So the derivative of this is going to be e to the t, which is itself, and then 3e to the 3t, and then 5e to the 5t. And now, to find the vector, the tangent vector, we are going to compute r prime of t at 0. So the tangent vector is going to be 1, 3, and 5. So that's the tangent vector. So now that I have a tangent vector, I have, so that's a tangent vector. What else do I need to do? No, that's it.
Yeah.
Just find the tangent vector. Now I can push it further and ask for the unit tangent vector. What now? Yes, divide this by its magnitude. So unit tangent vector would be 135 divided by the magnitude of 135, which is square root of 1 plus 9 plus 25. This is vector 135 divided by the square root of 35. That square root of 35 is almost square root of 36, so this is about, right, 6, and the numbers are about 1 over 6, 1/2, and 0.8, or 0.85, whatever. So the numbers are close to it, but that's the unit tangent vector. So you can rationalize this, right, and get root 35 on top and 35 in denominator if that makes you happy. But unit tangent vector, so we are going to denote the unit tangent vector as t with a hat, or t, and we have, I should rationalize this, so root 35 over 35, comma, rationalize, so 3 root 35 over 35, and then finally root 35 over 7. I think someone just said y.
What? Like
Oh, what? Okay. Well, that.
What?
That, yeah. You rationalize by square root of 35 divided by square root of 35. So the top root square 35.
And that should all add to 1, or what is
The magnitude of it. So if you square each one of these and take a square, add them and square, take a square root, they should add to 1 because it's a unit tangent vector. It's a unit vector.
Yeah.
And that's the lecture, guys. That's yes.
How can we do this if it asks for the tangent vector to add a component at a time?
You have to figure out between the function and the point at what time it happens. Yes. So if you're asked for the point, you will go back and you will figure out at which points, but which is actually setting each one of the functions with a t equal to the values from the point, right? And then you will calculate t. Just need to make sure that that t is the same for every component, because you can't have x component arrive somewhere at 2 seconds and the y component at 3, right? Good. Well, that's that. We will restart the stream for the next section. Take a few minutes break.